Assalamu alaikum everyone. My name is Arsalan Farrukh and I teach math and physics. In this video, I will be guiding you how to use the integration formulas in P3 exam. So here is a list of the formulas that's already provided to you in exam. You just have to learn to identify how to use these formulas. So if you have x raised to the power n, where n has to be a constant, so you can apply integration onto it, and that integration will get you x power n plus 1 divided by n plus 1. So if you have a power n, you increase the power by 1, and whatever number you get, you divide it by that number. That is for x to the power n. This is the formula that you are supposed to be learning in P1 exam. But this formula is not applicable for n is equal to minus 1. If n is equal to minus 1, it will become 1 upon x or x power minus 1. And if you try and apply this formula onto this, then you will get minus 1 plus 1, that is 0 in the denominator, that will cause this function to become undefined. So that's the only case where you cannot apply this power formula. And for that, you have another formula given to you, which is 1 over x integrates to ln x. Please note that in this formula, x is written in the modulus sign. The reason for that is because log does not exist of negative values. So this modulus sign represents that anything that is inside is going to be always positive. Another formula you have that is the easiest of the formulas, which is e power x integrates to e power x. And sin x integrates to minus cos x. Cos x integrates to sin x. And if you see sec square x to be integrated, that will become tan x. Now, if you look at all of these formulas very closely, you would also recognize that this is just the backward movement of differentiation. Like if you know that if you have x to the power n to be differentiated, then you multiply n and reduce the power by 1. So you're doing the opposite of that here. First you increase the power and then you divide it by that power. So all of these formulas that you have over here, they're basically the opposite of what you do in differentiation. Like e power x differentiates to e power x. So that means e power x integrates to e power x. Similarly, cos x differentiates to negative sin x. So that means sin x integrates to negative cos x. Like sin x differentiates to cos x, which means that cos x would integrate to sin x. Tan x differentiates to sec square x. So that means sec square x would integrate to tan x. Well, these formulas are already given to you in the formula sheet. But one important thing that you have to recognize or acknowledge is that there can be a small change made to the situation. That is, in any of these formulas, the x could be replaced by some linear function of x. That is, x could be replaced by something of the form ax plus b. That's a linear function because the x has a degree 1. The power is 1. It will never be anything other than that. So like you can get 2x plus 3 to the power 5 to be integrated, but you will not get 2x squared plus 3 to the power 5 to be integrated. And even if something like that happens, you can't really apply this formula. So the limitation is that every time x is replaced, it should always be replaced by some linear function of x. And that's only when you can integrate it by using these formulas. So the idea is that these formulas are given to you, but this is something you should be able to deduce yourself, that if in this formula x is replaced by ax plus b, so ax plus b, you still apply the same formula, you increase the power by 1, you divide it by n plus 1, but one other thing that you do is that you have to divide this expression by the coefficient of x. That's always an extra thing you have to do. This is also called integration by recognition. So you have to sort of recognize which formula is applicable in a particular situation, and then you have to apply that formula. Similarly, you know 1 over x integrates to ln x, but what if it's 1 over ax plus b? So you can see that x is replaced by a linear function. The formula doesn't change. It still is ln ax plus b. The only extra thing you have to do is divide it by the coefficient of x, which is a in this case. Similarly, e power x integrates to e power x. So e power ax plus b also integrates to e power ax plus b and also gets divided by a. Sin x integrates to minus cos x. Similarly, sin ax plus b integrates to minus cos ax plus b and also gets divided by a. Cos x integrates to sin x. So cos ax plus b would integrate to 1 over a sin ax plus b. And similarly, if the formula that's provided to you is sec square x integrates to tan x, then I would know that if it's sec square ax plus b, then it would be integrated to tan ax plus b, also divided by a. So that is how you have to apply these formulas. Now let's take a look at few examples, and we're going to initially focus on these three trigonometric formulas, how they can come in exam. So like for example, if I have to integrate sine of 3x, this is my question that I have to integrate. I know that it is not directly sine x, it is sine 3x. So x is replaced by a linear function. So I would recall that sine integrates to minus cos. So sine 3x would integrate to minus cos 3x. And the only extra thing that I have to do over here is divide it by the coefficient of x, which is going to be 3. So the final answer is going to be minus 1 upon 3 cos 3x. Every time I integrate, and it is an indefinite integration, so I have to put c as a constant of integration. Now similarly, I have to integrate cos half x. I can still compare it to the formula of cos x integration, which should integrate to sin x. So cos half x should integrate to sin half x, but I have to divide it by half. So 1 upon half simplifies as 2, and my overall answer becomes 2 sin half x plus c. Similarly, there is another example. I have to integrate 4 sec squared 2x dx. A constant 4 can always come out of the integral. So obviously I can just copy it as it is. Then I compare this with this formula that is provided to me in the formula sheet. And then I will be able to recognize that it is the same formula, but just that x is replaced by 2x. So I'm going to do 1 over 2 tan 2x, and then I will add a constant. In some cases, you have to sort of learn the method of integration, that this is what I would do if I come across this kind of situation. This is an example of that. If you have to integrate tan square, there is no formula for tan square given. There's a formula for sec square given, but you have to sort of recall that you already know an identity which says that 1 plus tan square theta is equal to sec square theta. So that means tan square theta would be equal to sec square theta minus 1. For this particular example, it will be sec square 3x minus 1. So I replace tan square. Every time you see an integral of tan square, you should think of this particular identity and replace it so that you get sec square, and you have a formula for sec square. So you integrate this term and this term separately. This will integrate to 1 over 3 tan 3x. This is integral dx. You can also look at it as x power 0, and x power 0 would integrate to 0 plus 1 upon 0 plus 1. That becomes x. And you can also look at it as integral and differential cancelling out, and you would be left with x only, and that's how you got an x here. So these are two ways of looking at it, and then plus c, the constant of integration. Moving on, there are other examples where we have to use trigonometric integration, but we also have to make use of the double angle formulas. Now, situation like this can somehow confuse you, and you might think of directly jumping to the formula of sine of integration, but you can't do that, because if I know that integral of sine x dx is cos x, so the only option I have, the only possibility I have of using this formula is that x is replaced by some other linear function of x, and then I would be able to use formula directly. I can't use formula directly over here because there's a whole square here. Since there's a whole square here, so I would not be able to use this particular formula. So I would have to get rid of this whole square. Remember that the sine square 3x is basically sine 3x whole square. So somehow the thing is that I have a whole square over this, and because of that I'm unable to directly use formula of integration. So for these kind of situations, you have to make use of the double angle formula. Like for example, if you have sine square 3x to be integrated, then you will go to the formula sheet and you'd identify that this is your double angle formula, which can be rewritten like this for cos square x and like this for sine square x. But since I have to integrate sine square, so I'm going to use this particular formula, that is rewriting the double angle formula, rearranging this formula, which is equal to 1 minus cos 2x upon 2. Remember that the structure of the formula should remain same, only the ratio of the angle has to be 1:2. So which means that if I have sine square 3x, I can double this angle and write it down as 1 minus cos 6x divided by 2. Once I would do that, then now the integration is going to be easier. I can take 1/2 outside. I have 1 minus cos 6x. And since I have 1 minus cos 6x, I can integrate 1 and cos 6x separately. The integral of 1 is going to be x. And cos 6x, I can directly use a formula that cos integrates to sine. So cos 6x integrates to sine 6x divided by 6, the coefficient of x. And then I'm going to just sort of simplify it after adding a constant. So this becomes half x and this becomes 1/12 sine 6x plus c. And that is how I would be able to integrate this. Similarly, I have another example where I have to integrate cos square half x dx. Now, I will use this form of this double angle formula to integrate cos square half x. So if cos square x is cos 2x plus 1/2, so if I have half x over here, I'll have the double of half x angle over here, which will be x. So this becomes cos x plus 1/2, and the rest of the working is very similar to the previous example. Take half common, integrate cos x to sin x, integrate 1 to x, and then multiply half to further simplify it. Moving on, I have another example where I have to integrate sine square 5x minus cos square 5x. I can take a slightly longer route and I can apply double angle formula on this sine square separately and this cos square separately, and that would work too. But I can also identify that one form of the double angle formula is cos 2x equals cos square x minus sine square x. There's a bit of an issue here. In formula, I have cos square x first, but here I have sine square. So what I can do is that I can take minus common, and that will make it look like this particular formula. And if it's comparable, you know that from x, you're getting 2x. So from 5x, you're going to get 10x. And then you will integrate cos 10x. That will be simplified to minus 1/10 sine 10x plus c. And that would be your overall result of this integration. Moving on, taking a look at another example where I have to integrate cos 4x minus sine 4x. I can first of all simplify this. I can take cos square whole square, sine square whole square, apply the formula. This is going to become cos square x minus sine square x and cos square x plus sine square x. I will recall a very basic trigonometric identity, that is cos square x plus sine square x is equal to 1. So this just goes away, and then I have to integrate cos square x minus sine square x. So by using double angle formula, cos square x minus sine square x becomes cos 2x. And then I can integrate it as 1/2 sine 2x. Cos integrates as sine divided by the coefficient of x, and then plus c, the constant of integration. Now, there is one more example I would like to mention over here, and that could be like if you have to integrate something, let's say like sine x cos x dx. So you would also recall there's another formula, there is another double angle formula, which is sine 2x is 2 sine x cos x. So if you see that there's a product of sine and cos, then what you could do is that you can take this 2 on the other side and you can replace this sine x cos x as 1/2 sine 2x. So then now you will be able to integrate it. Take half outside, then integral of sine would be cos 2x, and because there is a coefficient 2 over here, so I'm going to also divide it by 1/2 and then see. So that simplifies as 1/4 cos 2x plus c. Remember, you have to somehow, after understanding, incorporate some sort of learning towards integration. That if I have a particular situation, what do I do? So these are the situations that you have to sort of memorize, that if I have sin x cos x product, or if I have cos square x, or if I have sin square x, I'm going to have to use the double angle formula. Moving on to another example of the formulas we have, we know that it's given in the formula sheet that e power x integrates to e power x, from which we can deduce that if there is a linear function here, that is e power ax plus b, then that would also integrate to e power ax plus b. I'm just going to have to divide it by the coefficient of x, which is a. So this formula is directly usable. I have to integrate e power 3x, so that is going to become 1 upon 3 e power 3x. Or if I have to integrate e power minus x, that's going to become e power minus x divided by minus 1. And always add a constant of integration if there are no limits. Similarly, e power x plus 4 integrates to e power x plus 4. There's no point dividing it by 1 because it will remain the same. You can show that in your working if you want to. For another example, 6 just goes out of the integral. It's a constant multiplying. And then e power 2x integrates to e power 2x divided by 2, which I can further simplify as 3 e power 2x. Moving on with the examples, let's say I have to integrate e power negative x upon 2. It's also a very similar example. It integrates to e power negative x upon 2, and then I'm going to have to divide it by minus half. And then I add a constant of integration. This 1 divided by minus half simplifies to minus 2. One thing that is important, and please make a note of that you can't apply this formula unless the function is in the numerator. Here it's easier for you to shift it in the numerator, because if you have 1 upon a, you can just simplify that as a power minus 1. So when this goes up, its power gets multiplied by minus 1, and I get minus 3x plus 3. So this 3 comes from here. This is that same 3 that I've been copying throughout. But once I'm integrating it, e power minus 3x plus 3 integrates as e power minus 3x plus 3, but I'm going to also have to divide it by minus 3. And then I'll simplify it, and this is going to be my answer. Another formula of integration that you get in the formula sheet is 1 upon x dx to be integrated, and that is going to be ln x plus constant. And then again, this is something you have to figure out yourself, that if you ever get a situation where you have x being replaced by a linear function, the formula doesn't change. It still is ln absolute ax plus b, but you have to divide it by a. That's what you're going to do here. So if I have to integrate 1 upon 2x plus 7, I will say that 1 upon 2x plus 7 integrates to ln 2x plus 7. Since it's a linear function, I'm going to divide it by 2. And please keep in mind that if I had any power other than 1, like if I had 5x minus 2 whole square, then I wouldn't use the log integration here. This can come in exam and you would be required to do that. So if you ever get something like this, then that is the as power formula, minus 2 dx. And you would do 1 upon 5x minus 2, increase the power by 1, and then divide it by the new power. So that's your basic formula of integration that you need to be able to apply. This concept is only applicable when this power is 1 and not anything else. So here in this case, you can see 1 upon 5x minus 2 to be integrated. So here in this case, you can see 1 upon 5x minus 2 to be integrated, and to integrate this, you will be able to do 1 over 5 ln 5x minus 2. 8 upon 3x minus 4, 8 comes out. 3x minus 4 in the denominator integrates as ln 3x minus 4, and then you divide it by 3. Now we come to a very, very important example, and that's only applicable when you don't have a variable in the numerator. If there is some of that kind of situation, the formula is not directly applicable, first of all. Secondly, you should be able to recognize that if you have this kind of thing where your degree of numerator is either equal or greater than the degree of denominator, then you have to first simplify by using long division. So I've just did the long division, x divided by x minus 1. My quotient comes out to be 1 and my remainder comes out to be 1. So this becomes 1 plus 1 upon x minus 1. So that's going to be my expression. And now this is very easily integrable if I integrate the two terms separately. 1 integrates, or 1 dx integrates to x, and 1 upon x minus 1 integrates to ln x minus 1. It also gets divided by 1, but of course it doesn't make a difference, so you can skip writing that. Similarly, if you look at this particular example, you can't directly integrate it because you have a function in the numerator. So you will see that they have equal degrees, and then you have to simplify it by using divisibility. So I divided x minus 2 by x minus 4. 1 times x minus 4, I subtracted it, I got 2, and this becomes 1 plus 2 upon x minus 4. And once I would be able to identify that 1 integrates as x and 2, and this becomes ln x minus 4. So that is going to be my integral. Have a look at another example. This one is easier to simplify. You can just split the numerator. So it becomes x squared upon x and minus 1 upon x. This is x minus 1 upon x. X integrates to x squared upon 2, and 1 over x integrates to ln x. Now guys, have a look at another formula that's going to be given to you in the formula sheet. That is where you know that integral of 1 upon x squared plus a squared is 1 upon a tan inverse x upon a. So for this particular situation, you just have to sort of identify. It's again, as I said, all of the formulas are integration by recognition. So you have to sort of see if your integral looks like this, and then you can directly apply this formula. So the formula is 1 upon x squared plus a squared is 1 upon a tan inverse x upon a. So if it's a perfect square, that's fine. Like for example, if you have to integrate 1 upon x squared plus 9, you can write that down as 1 upon x squared plus 3 squared dx, and then apply the formula, and then you can say it's going to become 1 upon 3 tan inverse x upon 3 plus a. But if it's not a perfect square, even then you can work with it. Like for example, if you had to integrate 1 upon x squared plus 5 dx, no big deal. You can write it down as 1 upon x squared plus under root 5 whole square. So you forcibly bring in the whole square so that you can apply the formula, and then you can apply the formula 1 over under root 5 tan inverse x upon under root 5. That's how you have to apply this particular formula. So you can see one example is I have to integrate 1 upon x squared plus 4. I rewrote it as 1 upon x squared plus 2 square, and that becomes 1 upon 2 tan inverse x upon 2. Looking at another example, I have 1 upon 4x squared plus 9. So now this 4x squared can be written down as 2x whole square, and then I will recognize it as a situation where x is replaced by some linear function. My formula doesn't change. I still apply the same formula, but the coefficient of x gets divided. So this is going to be 1 upon 2 because the coefficient of x is 2, and then 1 upon a of the formula. In this case, a is 3, so 1 upon 3 tan inverse x upon a, which is 2x upon 3. There can be a question, this could be the hardest form of the question, where you have been given a situation and you might have to use the completing square method. So if you have been given something like this, you first apply the completing square that you learn in AS. You will recognize 4x squared as 2x whole square, 12x as 2 times 2x times 3. And to balance this out, you add 3 square and subtract 3 square, and then you copy this 34 as it is. This whole working is done so that you can apply a whole square formula onto this, and you can write it down as 2x plus 3 whole square. And this simplifies as 34 minus 9, which should be 25. So I can write 5 square in place of 25, and then now I'm ready to use the formula. So the formula is what? That x squared plus a squared is 1 upon a tan inverse x upon a. X is replaced by 2x by plus 3. So I will just divide it by the coefficient of x, 1 upon a tan inverse x, which in this case is 2x plus 3 divided by a, which is 5, and then plus c. So guys, this brings us to the last formula of integration, which comes from this formula of integration, which is 1 over x dx ln x. We've already said that x could be replaced by ax plus b, and we're going to integrate it as 1 over a ln ax plus b. One more thing that is part of our syllabus is that only in this specific example, this x could be replaced by some function which is not necessarily the linear function. It could be any function of x. You can still apply the formula, but you just have to make sure that whatever function here is, its derivative is there in the numerator. So again, it's integration by inspection, and if you ever come across a situation where you see a function and its derivative on top, then you can directly apply this formula. This formula is given to you in the formula sheet. You just have to recognize a derivative of function divided by function integrates as ln of that function, and then you add a constant of integration. So like, for example, if I look at this question where I have to integrate x upon 1 minus x squared, first of all, I can't apply the whole power formula because this function has a whole power of 1, and that's where the power formula is not applicable. This is log formula that I have to apply here. But this is also not a linear function. I could do that if there was a linear function. I could do that directly without x being there. Like, for example, if I had 1 upon 2x minus 1 dx, I could do that integration directly. But here I have 1 minus x squared and x in the numerator. So what I'm going to do over here is that I will compare this with this function, and then I will see that what is its derivative. I have to work out the derivative of this function. So I can just pick this function out and maybe do a little bit of rough working and identify that 1 differentiates to 0 and x squared differentiates to minus 2x. So the derivative of this function is minus 2x. And I will be like, I have x in the numerator. I don't have minus 2. Again, one more important thing about integration is that you can move constants in and out, but you can't move variables in and out. So what you do is that you multiply and divide it by minus 2, and the numerator minus 2 you move inside, so that the numerator becomes exactly the derivative. So you have a function, you have its derivative, and this minus 1 upon 2 has been brought in here to introduce this minus 2 inside, so that I have a derivative appearing in the numerator. So this minus 1 upon 2 copies down as it is, and if this function's derivative is here, so this becomes ln 1 minus x squared. I directly apply the formula. So the key is I have to always see that I have derivative up and I have function down, and then I will be able to integrate it. Similarly, if I look at this particular example where I have to integrate x squared upon x cubed plus 8. So I just roughly differentiate x cubed plus 8, and I recognize that that is 3x squared. I have x squared, only 3 is missing. That can be introduced. If there was no x squared over here, or let's say if there was only 3 here, I could not introduce x squared. And then there's like sort of a deadlock situation. I could not integrate it. And hence, obviously, this kind of question would not come in exam. But since x squared is already provided and only 3 is missing, so I can multiply and divide by 3 so that this function is directly the derivative of it. And this, once I apply the formula, you have to make a note. This derivative just vanishes once you apply the formula. So there is no derivative. There's just this function written down with ln. This formula is given to you in the formula sheet. You're not learning any of the formulas. You're just learning how to use them by recognition. So if I have a derivative and a function, I can directly write it down as ln function. This 1 over 3 was brought in for adjustment, and it will stay there. Let's have a look at another example. I have to integrate x plus 1 over 2x squared plus 4x minus 1. And I recognize that if I differentiate this, this differentiates into 4x plus 4. I have x plus 1. If I multiply it by 4, then it becomes 4x plus 4. So I have multiplied and divided it by 4. And that will give me the derivative in the numerator. So these questions are going to be specifically designed in a way to help you bring it into that form. Because if there was, let's say, x plus 2, then it was not directly becoming the derivative. If I'd multiplied it by 4, it would not become the derivative, and I would not be able to integrate that. So the question would be like this, that you can only make some minor adjustments by multiplying and dividing by a constant, and you will get the derivative. So function and its derivative there, so its integral is going to be ln of that function. Moving on, looking at another example, I've already mentioned that there is a bit of a learning involved in integration, and that applies with the integration of cot x and tan x as well. There are no formulas to directly integrate cot x or tan x. So remember that every time you see cot x, you will rewrite it as cos x over sin x. Every time you see tan x, you will rewrite it as sin x over cos x. Now that does one thing for you. The derivative of sine is cos. So if I can see this is the function and its derivative is there, so I can write ln function plus c, and that will be my one-step integration. Very similar if I have tan 2x and I rewrote it as sine 2x over cos 2x, but I would recognize that the derivative of cos 2x is not just sine 2x, it is negative 2 sine 2x. But then again, a negative 2 can be easily brought in. So I would multiply and divide it by minus 2. And once I'll do that, then I'll have its derivative, cos 2x's derivative in the numerator, and I'll write the formula down, which is ln of that function that I see in the denominator. Another very simple example, I have to integrate cos x over 1 plus sine. See, how to apply the formula is very easy, but you have to sort of know that, like, in a particular situation, which formula do I have to go to. So like 1 plus sine x's derivative should be cos x. So I have its derivative directly there. I can directly apply the formula. Similarly, 1 plus ex's derivative would be just ex, which is already there. In one step, I can apply ln 1 plus ex. Moving on with another example, sometimes it's a little tricky. You have to make some minor adjustments to be able to clearly view that the derivative is there. Like if this x in the denominator, if I write it in the numerator as 1 over x, then I would be able to recognize that the derivative of ln x is 1 over x, and that derivative is there. So I can say this is going to become what? Ln x plus c. Let's take a look at another example. I have to integrate this. If I look at only this part of the function, its derivative is 1 upon 2 root x. So this root x goes up, it becomes 1 over root x, but there had to be another 2 as well. So I introduced a 2 and multiplied it by 2 so that it cancels out. This function's derivative is there in the numerator. So integral is going to be ln of that function. 2 comes from the previous step. Similarly, the derivative of tan is sec square, so the integral is going to be ln tan x plus c. Sometimes again, as I said, I mean, there could be some trickier question and have to make some more adjustments with that. Like for example, I had 1 minus x whole square over 1 plus x square. So it was not very directly integrable, but I first of all expanded it 1 minus 2x plus x square, then 1 plus x square minus 2x, I sort of separated them out. So 1 plus x square over 1 plus x square is something that we write down as one term, which will become 1, and 2x upon 1 plus x square as another integral. The good thing is that 1 can be integrated directly, and for this function, its derivative is right over there. So I can just see that 1 plus x square differentiates to 2x, so it becomes ln 1 plus x square. Some cases I have to make more adjustments. Again, you would sort of recognize that here the degree of numerator is bigger than degree of denominator. So I'll first of all simplify it by the process of long division. I took minus common, so it becomes in the descending order, and hence that eases up my divisibility. I divided x square minus x plus 1 by x minus 1. I've already posted a video before regarding how to do synthetic division and long division. If you have issues with that, please watch that video. So x square minus x plus 1 divided by x minus 1. My first term of the question is going to be x. X square minus x is what I get after multiplying this. And once I minus these, this completely cancels out. I'll be left with 1. So this becomes x plus 1 upon x minus 1. X plus 1 upon x minus 1. And then I can integrate them separately. X integrates to x square upon 2, and 1 upon x minus 1 integrates to ln x minus 1. So guys, this was all about using the formulas of integration. If you sort of memorize all of these situations, you should be able to apply these formulas more effectively. I hope you liked the video and if it was helpful. Kindly please give a thumbs up and subscribe to my channel. I will put down the link of notes, worksheets and work solutions in the description. Thank you.